This morning I would like to continue with the lecture on forward and inverse modeling, and we've already touched upon this a few times. So the outline of today's talk is that I'll first start with a short motivation and a background, and then there's basically two large sections, one section on forward modeling and one section on inverse modeling. And in each of these sections I will deal with the detailed concepts of forward and inverse modeling. But let's start with the motivation and the background. So if we look at EEG and MEG, then of course the strong points of it are that it has a very high temporal resolution, so it allows us to track brain activity really fast. With this high temporal resolution we can characterize individual components of event-related potentials, we can look at oscillatory activity, and we can disentangle the dynamics of cortical networks. But the weak point of EEG and MEG is that it's a measurement on the outside of the brain, and therefore that we have overlap of components. So you could say we have a relatively low spatial resolution, and especially if you compare it with hemodynamic methods such as fMRI. The second motivation for doing source modeling is that if you find an ERP or an event-related field, you want to characterize it in its physiological terms, and the time or the frequency are the natural characteristics of your recording, so they directly relate to the cortical activity, whereas the location requires an interpretation of the scalp topography. And forward and inverse methods are available to help you to interpret this topography. Furthermore, forward and inverse modeling helps you to disentangle the time series, and that's especially important if you are interested in activity from multiple sources at the same time, or are interested in networks. So let's again look at the superposition of source activity. This is a slide that I showed yesterday. So if we have a source at the back of the brain, and if we have a simultaneous source at the front of the brain, and we know that a channel that's more or less in between will pick up activity from both sources. Channels at the back will primarily pick up activity from the occipital source, and channels at the front will primarily pick up activity from the frontal source. But it's not only activity from the frontal source, from the posterior source. Like there's always overlap of these sources on the channels that we're recording. So what we have is a varying visibility of each source to each channel, and the time course of each source contributes to each channel. And this contribution of course depends on this visibility. But it's always important if you're looking at your data that the activity at each channel is a superposition of all source activity. So even though there's a very small contribution from other sources, at the channel level you always have the superposition. If we now look at source modeling from an overview, what we have is we have the tissue of the body. In this case it's the tissue of the head. And this is electrically conductive. And what we have is we have physiological sources in the tissue of the body. In the case of the head it's the neurons. And these physiological sources, they are capable of producing electrical currents. These currents will flow through the tissue of the body, through the head, and that gives rise to a potential or field that we can observe. If we start in modeling sense from the physiological sources and make predictions of how the observation will look like, that's what we refer to as forward modeling. Whereas if we start from the observation and try to infer what the underlying physiological sources are, that's what we call inverse modeling. And in general, you will be interested in inverse modeling, because in general you will be working with observations, like with real data. But you cannot do inverse modeling without first doing the forward model. So that's what I'm first going to focus on, forward modeling. Forward modeling requires a number of ingredients. It requires a source model and it requires a volume conduction model. Yesterday we've seen the tissue that produces the electric current. So we have the pyramidal cells. These pyramidal cells are nicely aligned. And if we have action potentials arriving at the synapses, then we have currents flowing along the dendritic tree. And these currents, they basically produce electric currents which flow through all the tissue. Of course, this is a very microscopic view. And if we zoom out a little bit, then what we have is a piece of tissue where, in principle, each of the dendritic trees can be modeled with an equivalent current dipole model. And an equivalent current dipole model is a mathematical concept, and it's a It's a description of two poles, like a positive and a negative pole. You can think of this as a battery. And it's an equivalent current dipole model because it produces a current that is equivalent to the current that would be produced by a neuron. So it's a simplification of the neuron, but it's a very useful building block. However, what we do is we don't model each individual neuron separately because we don't have that spatial resolution. So what we do is we take a column and we say, well, all of these small equivalent current dipoles, they can be simplified using a single larger equivalent current dipole. And that idea we can take further. So we can also look at a piece of cortical sheet where each of the columns in itself can be represented as a equivalent current dipole. And again, we can simplify this by taking one larger equivalent current dipole. And actually, relatively large patches of cortex can be modeled like this. That's because we're recording from quite a distance. So we don't see this small detail in a cortical sheet. There are some cases, however, where you have to be aware that the model starts failing. And that's, for example, if we have a folded piece of cortex. Because if we have a folded piece of cortex, if we describe the activity along the cortex with a single equivalent current dipole, and what happens is that the center of mass of this equivalent, so that the location of this equivalent current dipole will describe the center of mass of all the activity. And that might mean that it's displaced relative to the curved surface that we have here. Okay, so besides the sources, we also need a volume conductor. And for the volume conductor, we have different options. We can either take analytical or numerical solution for the volume conduction model. The volume conduction model describes the electrical properties of the tissue. It also describes the geometry, like how does the shape look like through which the currents flow. But important is that it describes how the currents flow, but not where they originate from. Like the currents originate from the sources, and the volume conduction model is basically just a passive conductive device. And in fact, we can use the same volume conduction modeling for EEG and MEG as we are using for transcranial direct current stimulation or transcranial alternating current stimulation or magnetic stimulation, where of course the currents are being produced by an external stimulator. The simplest volume conduction model that was introduced in around the 80s is a spherical volume conduction model, because the head can be modeled reasonably well with a sphere. And the nice thing about a spherical volume conduction model is that it's simple and that it's analytic, so we can compute it with an arbitrary accuracy. But of course it's not very accurate if you consider how well the sphere fits the head. So that's why we also have developed volume conduction models that allow for realistic geometries. And the one that is most used, especially in EEG, is the boundary element method, the BEM. Furthermore, we have the finite element method and we have the finite difference method. And let me shortly explain more or less what the differences are between them. One of the striking differences is in how they describe the geometry. With a boundary element method, the geometry is described by boundaries, by surfaces, and these surfaces are described using small triangles. Whereas the finite element method is usually working with tetraeders, like small volume elements with 4 corners, like it's a pyramid, but then only having 4 corners rather than 5. But the finite element method, but also the finite difference method, they can also use hexaheders, like small cubes, like voxels. Let's look in detail at the boundary element method. In the boundary element method, we're making the assumption that the head is comprised of multiple compartments, and each of these compartments is assumed to be homogeneous. So that means that the conductivity is assumed to be identical throughout the volume, and isotropic, which means that the conductivity does not depend on the direction in which the current is flowing. And these are simplifications because we know that in white matter, current will flow slightly easier along the white matter tracks than across the white matter tracks. We have some important tissues that we normally consider in a model, and that's the skin, the skull, and the brain. So what we often do is we just say, well, we have 3 tissue types, and these 3 tissue types, they really have different electrical conductive properties. And sometimes if we make accurate models, we will also consider the CSF, like as a very thin layer between the brain and the skull. Okay. Perhaps I should point out that if I'm saying brain here, it's basically everything, that all the tissue that's contained within the skull. So it's white matter plus gray matter. And like what we're assuming here is that all of this tissue contained within the skull has a homogeneous conductivity. So what we do is we describe the surfaces between these tissue types. We describe it with boundaries, and for that we use triangles. And the nice thing about triangles is that we can make arbitrary complex shapes out of it. So we can use triangles to describe a cube or a sphere, but we can also make a surface like this. So the nice thing is triangles are just very flexible in describing closed surfaces, which is a requirement for the boundary element method. So the procedure that we use for the boundary element method is that we start with an anatomical MRI, and we segment this anatomical MRI in the different tissue types. So for each of the voxels, we assign a value, like an integer value, saying whether it's brain, skull, or skin. And what we subsequently do is that we extract the surface descriptions describing the boundaries between these tissue types. And what we then do is we typically will downsample these surface descriptions to a reasonable number of triangles to keep it computationally feasible. Once we have the geometry and once we have assigned the conductivity to each of the three types of tissue, what we do is we compute the model, and the computation of the boundary element model can be done independently of the source model. So that basically means that you don't have to specify what kind of dipoles you're going to work with. You just have to do this computation once, and then you can store the results on disk. So in this computation of this boundary element model is a lengthy computation, like it can take half an hour or so, but it's only something that you have to do once, and then while you're doing your computations on the real data, it's actually a very fast method. If you're doing your anatomical processing with sufficient detail, then you can actually make your boundary model almost arbitrarily complex. So you can also include ventricles in your boundary element model. And you can also include holes in the skull in your boundary element model. But it's relatively uncommon, and it's relatively challenging to make the anatomical models so detailed. So that's why most people that are using boundary element model actually restrict themselves to 3 or 4 compartments. A second model that we can use for the volume conductor is the finite element model. And with the finite element method, we tessellate the 3D volume in small tetraeders, or in small volume elements. And that means that rather than describing the surfaces, we actually describe the whole volume. And that means that we also need a large number of elements. The finite element method allows us to simplify the tessellation to make larger volume elements in regions where we need less accuracy, for example, deep in the brain, and to use more tetraeders, more volume elements, and in regions where accuracy is more required, for example, around the skull. The nice thing about the finite element method is that each tetrahedra can have its own conductivity, and that conductivity can also be anisotropic, so can also be direction specific. And that makes the finite element method the most accurate numerical method that we nowadays have for computing the forward problem. However, its computation it's very expensive. Like it takes a lot of time to do these computations, and that means that at this moment it's not used that much. We're working together with the Symbio team in Münster on making the finite element method more applicable to real world data. So with FieldTrip we're trying to make the finite element method more like generally used, because it's really an important step forward. The third method that I used for numerical solutions for the volume conduction problem is the finite difference method. And the finite difference method is very easy to compute, but it's not very useful in practice. The reason for me including it here is because it's very intuitive, so I can really use this one to explain you how volume conduction modeling works. So if we look at the finite difference method, then what we do is we describe the brain, or the head, in terms of voxels, in terms of small cubes. And in each cube we describe the center, and what we can do is we can look at this cube and its neighbors. If you consider such a cube, then you can imagine the cube being connected with its neighboring cubes with a small resistor. And basically the whole brain is the whole head consists of these elements that have some resistivity to their neighbors. Okay, so this resistor network is actually something that we can work with, because on such a resistor network we know that we have Ohm's law and we have Kirchhoff's law. Kirchhoff's law states that all the current that flows in the network also has to flow out. Basically, there's no current being generated inside the network. So the sum of the current over all the resistors has to be 0. Well, furthermore, we have Ohm's law, and we can combine these two in this equation. So basically, the potential difference over each resistor, when added up, has to sum up to 0. And of course, we can fill out the potential differences. And that gives us one equation. So this is one equation for this node that relates this node to its neighbors. So that means that with the finite difference method, we have an unknown potential at each of the nodes, and we have a linear equation for each of the nodes. So if we now assume that the head is described with 100 by 100 by 100 voxels, that means that we have 1 million linear equations. But we also have just as many unknown potentials, so that means that we have a linear system that we can solve. So this is just for the passive conductive properties of the tissue. So what we then do is we say, okay, the sum of the currents is 0 for all the nodes except for one node where we allow some current to be generated, and for another node where we allow that current to be drawn out of the network. So we specify the current like a positive current for one node and a negative current for another node. And what we then do is we solve for the unknown potential. So this is very simple. Like, this is something that you could do with your high school understanding of mathematics and of physics. But it's a very inefficient method because the computation of the potential distribution depends on where the source is. So it's really like you have to do it for every possible source configuration, and it also requires a lot of memory. FieldTrip implements a number of different methods for volume conduction modeling. And what we in general would do is we would start with FD read MRI. So we would read the anatomical MRI from disk. And then after aligning the anatomical MRI with the coordinate system of the recording device, of the MEG or EEG recording device, we would call FD volume segments to extract the brain, the skull, and the scalp. And then subsequently we call FD prepare mesh to make triangulated surfaces for the brain, the skull, and the scalp. And what we can do is we can specify for each of the surfaces how many triangles it should have. And although it's nice to have a scalp surface with a lot of triangles because it looks nice, it's more important to have a brain surface with a lot of triangles, because on the brain surface, like on the inside of the skull, that's where the potential varies most rapidly. Whereas on the scalp, the potential actually doesn't vary that rapidly anymore. So if we assign the number of vertices, then typically we will assign more vertices to the surfaces where we have a rapidly changing potential. And what we then can do is, like, if we have these meshes, we can either use config methods concentric spheres using FD prepare head model. So what this will do is it will just fit 3 concentric spheres, one to each of the surfaces. So that allows us to use the analytic solution for the EEG. We can also use a number of boundary element methods. BEM-CP is a Christoph Philips BEM implementation. It's available in MATLAB. It also works on all the platforms relatively easily, relatively robustly. We also have OpenMEG implemented in FieldTrip. OpenMEG is a little bit more difficult to install on your computer. Like, it depends on external binaries. So it works relatively smoothly on Linux, but on Windows I've heard that it's a bit more difficult to install. But it is a more accurate method. Like, it's a more accurate implementation. And if you want to use a finite element method, you would specify config method is Symbio, and you would again call FD prepare head model. Although for Symbio, you would not use 3 different meshes, but you would actually use the full tessellation of the whole brain. Okay, so far I've been explaining the sources and the volume conduction model, but I haven't really been mentioning whether it's for EEG or for MEG. So let me detail a little bit on what the differences are and the similarities between EEG and MEG. If we consider EEG, then we know that we have cortical tissue. That cortical tissue is activated, and that cortical tissue produces currents, volume currents that are flowing through the tissue of the brain, through the skull into the skin. And if we then apply electrodes to the skin, we can record these currents as a potential distribution between these electrodes. So that means that with EEG we're recording the potential that is due to the volume currents. And the potential difference between the electrodes corresponds to this current flowing through the skin. But actually the skull is very poorly conductive. So only a very small fraction of the current will flow through the skull into the skin. And in order to model this current properly, we have to model the skull and the skin as accurately as we can. So the skull and the skin are really important for EEG volume conduction modeling. If we consider MEG, then we again have the same cortical tissue that is generating, that is active, and that activity is reflected in the primary currents of the cortical tissue. And these primary currents, they produce a magnetic field according to the right-hand rule. And this magnetic field can be measured on the outside using MEG sensors, magnetometers or gradiometers. So with EEG we don't see the primary current, we only see the secondary current. With MEG we see the magnetic field of the primary current. However, with MEG we also have the magnetic fields of the secondary currents. Like at the same time as the primary current is flowing, there will also be current flowing through the whole tissue, and they also produce magnetic fields. So with MEG volume conduction modeling we measure the magnetic fields due to the primary current, but also due to the secondary currents. And it's these secondary currents for which we need volume conduction models. Only a tiny fraction of the currents actually passes through the poorly conductive skull, and therefore with MEG we typically neglect the skull and the skin, because there's a very small amount of current flowing there, so they contribute only a tiny fraction to the MEG distribution. So that means that with MEG we can use a simpler volume conduction model, and that's convenient. And it's especially convenient because with the imaging methods that we have, like with anatomical MRI, it's just not so easy to get a good contrast in the skull and a correct description of the skin. Like MR methods, of course, they're mainly being developed for imaging the brain, so we have nice contrast in the brain, but skull and skin are difficult to segment and difficult to model. However, if we consider EEG and MEG, we use the identical source model. So for both we are using the equivalent current dipole model to describe the sources. And we use a very similar volume conduction model. So the principle behind the volume conduction model is actually the same. And important is that these same inverse methods apply both to EEG and MEG. So that's also the way that we've implemented in FieldTrip. Like you can use an arbitrary volume conduction model with an arbitrary inverse method. Like they can be mixed and matched. Of course, some of the inverse methods have certain strengths or certain weaknesses. So that means that not all the inverse methods are equally applicable to EEG or to MEG. But that's not a mathematical consequence, it's more a consequence of the assumptions made in the inverse method. With MEG we're measuring magnetic field, and we can measure magnetic field with only a single sensor. With EEG you're always measuring potential differences. So for EEG you always have to consider the referencing scheme, and the referencing scheme that you use in your data has to be consistent with the referencing scheme that is used in the model. And for EEG volume conduction modeling, what we in general always do is we use a common average reference. And the reason for using a common average reference is that it averages out the error over all the electrodes. So that means that if you want to do source modeling on your EEG data, and somewhere along the pipeline you should compute a common average reference of your EEG data. That's just something that you have to keep in mind. Okay. I've gone over the forward modeling, and now I would like to go over the inverse modeling. So forward modeling is required to, like it's mainly the domain of physicists like me, explaining how the potential would look like given a model for the sources. Inverse model is like given the observation, how do we interpret it? And before I want to show you how these methods on inverse modeling work, I want to give a demo. And we had a little bit of difficulty with the audio, so we're going to play audio from that computer over there. Okay, let's start. So this is a fish. This is an elephant fish. It lives in the Nile, and it lives in very muddy water. And that one is a little bit ahead of this one. But what you can see, like besides the long snout, is that it has an organ on its side, and with that organ it's able to emit small electrical pulses. And what we did is we put such a fish in a fish tank, and we attached an EEG system to it. So what you can hear are the small electrical pulses when this fish is sensing its environment. So basically, it's rather than using echolocation, which bats use, it's using electrical navigation to sense its environment. It senses like a small prey that he catches, but it's also senses in its environment for the shape. You can see on the system that it's not really a state-of-the-art EEG amplifier. Like these recordings were done about 15 years ago, and back then we used a really old EEG system we had standing around. But it's a 64-channel EEG system, and the nice thing about this EEG system is that we hooked it up to a computer, and we were able to record this data, but also process this data in real time. So like 15 years ago, we were already doing real-time processing of EEG data. So every time that the elephant fish emits a small pulse, we can detect it and we can measure the field distribution on the fish tank. And what you see here is on this computer, you can see how we source reconstruct the position of the fish. And there's a number of things that we're doing in the source reconstruction. Let me wait a second. So we're determining the location of the fish, and we're determining the direction in which the fish is swimming. So what you see here is like a top view, a frontal view, and a side view of the fish tank. And over here is just for reference is like the thermometer. Like otherwise it's difficult to distinguish left from right. So every time that the fish gives a pulse, we measure the potential distribution and we make a forward model for the fish as an equivalent current dipole. We compute how the potential distribution would look like, and then we move the fish around, like the model fish around, until the potential distribution matches the one that we recorded on the tank. Of course, this is a very artificial situation. Like normally we don't know where the fish is. Like normally we don't know where the activity in the brain is. But actually here we can very easily check that the source reconstruction method is working fine. Okay, so there's one more thing which is different here than what we have in the brain. Here we only have a single fish. Whereas in the brain we typically will have activity at multiple sites, and actually we don't know a priori how many locations we would have activity. So the challenge is that with source modeling, you would have to imagine that you would put a cloth over the fish tank. You don't know where the fish is, and you don't know how many fish there are in the tank. So that's the way that you should think about source modeling. Can you stop it again? Thanks. Okay, so we have a number of inverse methods that help us to locate activity. The simplest one, and the one that also was initially invented, is using single and multiple dipole models. And the idea with dipole modeling is that we try to minimize the error between the model and the measured potential or the measured field. We also have distributed models, where we know that we have a perfect fit of the model to the measured potential. And that requires us to make additional assumptions on the source, such as smoothness or minimizing the power of the source or minimizing the amplitude. And a third family of source reconstruction methods is spatial filtering. And with spatial filtering, we're not trying to fully explain the topography, the measured topography, but we're scanning the whole brain with a single dipole. And for each location, we're trying to estimate source activity independent of all the other locations. And spatial filtering methods, very well-known class of spatial filtering methods are beamforming, which comes in different terms like linear constraint minimum variance, or synthetic aperture magnetometry, or dynamic imaging of coherent sources. And this afternoon, Svetlana is going to give a much more detailed lecture on beamforming methods. And another way of doing spatial filtering is using multiple signal classification. We have a number of these methods implemented in FieldTrip. Like there's many different methods and many different versions of it. Like not all of them are implemented in FieldTrip. But what you normally would do is in FieldTrip you would pre-process your data, and then after having constructed the volume conduction model, you could call FD dipole fitting, or you would call FD source analysis, where you would specify config method as minimum norm estimate, where you would specify config method as dynamic imaging of coherent sources, or linear constraint minimum variance beamformer. The reason for pooling these three methods together in a single function is that they all require a description of the sources on throughout the whole brain. The beamforming methods, themselves are not a distributed source method, but we typically apply them for a grid that covers the whole brain or the cortical sheet. Whereas dipole fitting really returns the estimates at only a few points, so the interface is a bit different. So let me now go through each of the source reconstruction methods in detail. With single or multiple dipole models, what we do is we manipulate the source parameters to minimize the error between the model and the measurement. And the source parameters that we can manipulate are the location of the source, like the location of the fish, the orientation, and the strength. And the orientation of the strength, they together correspond to the dipole moment. Like we can describe this as a vector, and the vector has a certain orientation, and the vector has a certain length. So quite often what you will see is that the dipole moment will be described, where dipole moment refers to orientation and strength together. Dipole moment relates linearly to the field distribution, can be estimated linear. Position is estimated nonlinear. So that's why we typically separate position from dipole moment. But the important thing for you to remember is that with multiple dipole models, what we're doing is source parameter estimation. And you all know parameter estimation quite well. Because parameter estimation is something that you do if you just have an independent variable and you've made measurements giving you the dependent variable. And what you can do is you can make a model that describes the dependent variable as a function of the independent variables plus a number of parameters. And these parameters A, B, and C are basically the things that we're trying to determine using source modeling. The parameters that we're estimating with dipole fitting are, for a source with a few parameters, is the position, the orientation, and the strength. What we do is, given the position, orientation, and strength, we compute the data model and we minimize, we repeat this and minimize the error between the model and the data. So what you should think of is that we have our data and we determine a model where parameter A and B are the parameters that we're actually interested in. So those are the parameters that you would report in a publication if you've done source modeling. But of course not with a linear model. So if we now look at the superposition principle, which I've touched upon yesterday. So if we have multiple sources that are simultaneously active in the brain, then we know that the potential distribution of these three sources simply adds. So the combined potential distribution of multiple sources is just the sum of the potential distribution of each of the individual sources. And that's very convenient, because that allows us to keep the orientation, describe the orientation as a consequence of three independent dipoles. So what we can do is we can take three dipoles, one pointing in the x, one pointing in the y, and one pointing in the z direction. And for each of these three dipoles, we can compute a potential distribution. And then the combined potential distribution is basically a linear mixing of these three. So what we have is a dipole moment in x, y, and z direction. And with those three, we can model a vector representing the dipole. The combined potential distribution is the strength along the x, the y, and the z direction multiplied with the respective potential distribution. And that's something that we can write like this. So this is the number of channels by 3, because we have 3 potential distribution for each, one for each of the sources. And this basically is the description of how strong is the dipole in each of the 3 directions. So this is a linear system, and that's a linear system that we can solve. So L is usually referred to as the lead field matrix, so the gain matrix, and L times Q should correspond to the measured potential. So what we can do is we can say, well, the measured potential is we model the measured potential as a multiplication of L times Q, where L depends on certain source parameters, and the source parameters here are position, because the strength is already in Q. So this is where the strength and the orientation are in. And what we then can do is we can take the pseudo-inverse of this matrix and multiply it with the data, and that gives us the source strength. So this is usually referred to as decoupling, like we're decoupling the estimation of the position parameters from the estimation of the strength parameters. This is like a very fast computation, and it will always result in optimal strength. However, for estimating the position, that's more challenging, because the potential distribution depends non-linearly on the position. So what we do is we take our measurements, we take our model, where the model depends on certain parameters, position parameters, and for each of the channels, so like index I indicates the channel, for each of the channels we compute the difference, we square it, and then we sum it. That gives us the sum of squared errors. And if we would plot the sum of squared errors as a function of the parameters that we have, like the position parameters, then we could consider this as an error landscape. Like for certain locations in the brain, like if I position the dipole at certain locations in the brain, the error will be smaller, and if I position the dipole at other locations, the error will be larger. Because what we're interested in is finding the location in the brain where the error is the smallest. Okay, so how do we find this position? Well, there's two strategies that we're combining. The first strategy is using a grid search. Like we can in principle compute that error for all the locations in the brain. And if we consider a single dimension, for example, along the medial lateral axis, and if we consider that we compute the error for 100 positions along that axis, well, that's doable. But then if we consider two directions or three directions, that means that there's easily 1 million locations at which we would want to compute this error. Let's imagine that a single computation takes 1 millisecond. Then this is still 1000 seconds, which is about 20 minutes. Well, 20 minutes is doable. But the problem arises if we have two dipoles. Because if we have two dipoles, then suddenly we have 10 to the power of 12 different configurations that we have to consider. So it's not 20 minutes anymore, but it's like it's an infinite amount of time. So that means that using a grid search approach, we cannot locate multiple sources. We can only locate a single source. And that's why for source models with multiple sources, we need another strategy. And that strategy is basically a gradient descent. So what we do is we try to manually, or using a very coarse grid search, we try to place the dipoles more or less in the right region. And then given a certain position, we compute how the error is going to decrease or increase if we move the dipole around a little bit. And that's something that you can imagine like walking in the mountains on a very foggy day, like you can't see very far, and you want to go to the valley. So you can only see a few meters around you, and what you can do is you can look in the direction where it's going downhill, and then you walk in that direction, and you will see a little bit more, and then you walk in that direction. So that's what's happening with the gradient descent optimization. Or if you imagine doing this type of walk in the mountains, you realize that there's no guarantee that you're going to end up in the valley. So you might end up in a local minimum. So what we do with gradient descent optimization is that we try to both make large jumps and small jumps. So like we try to jump over these small hills in order to get these minimal locations. Furthermore, what we often do, like very pragmatically, is that we will start with multiple initial estimates and then have all those initial estimates converge to a minimum. If all the different initial estimates that we start with, if they all converge to the same minimum, then we can be more confident that the minimum is a global minimum. But there's no guarantee that it's going to be a global minimum. So that means that with dipole fitting, with nonlinear optimization in dipole fitting, there is quite a dependency on the initial estimates that you start off with. If we consider the brain, then actually we could also say, well, the brain is not a number of not a small number of cortical patches that is active. We could also say, well, the brain is basically this cortical sheet, and there is potentially activity all over the cortical sheet. So what we can do is we can also describe the brain using a distributed source model. And with distributed source models, what we're doing is we're not estimating the position of the source, because we already know where the source is, like it's in the gray matter. And we start with a predefined grid, like a 3D volume, or more typically would use a cortical sheet describing gray matter. And what we do is we estimate the strength at each of the grid nodes of this cortical sheet. And that is in principle easy to solve. However, we have many more unknown parameters, like the strength at all these grid points, than we have measurements. And the consequence is that an infinite number of solutions will be capable of explaining the data perfectly fine. And that means that we need additional constraints to find a unique solution. But in principle, distributed source modeling is just a linear estimation problem. The type of models that we use for distributed source models are usually like this. So like usually we take a cortical sheet. We typically use FreeSurfer to extract a cortical sheet. And if you zoom in on such a cortical sheet, then what you see is that it consists of many triangles. And for each of these triangles, what we do is we say, well, we're going to model the activity of that triangle using a dipole, an equivalent current dipole. and we can impose an orientation constraint. Like if you have done your co-registration and your anatomical modeling very accurately, then we also know that the current will be perpendicular to the surface of the cortex. However, if there's some inaccuracies in your geometrical model, then that assumption might be too stringent. So sometimes you will see people restricting orientation to be perpendicular to the surface, and sometimes you will see that people allow the current dipole to be rotating all over the surface. As before, we have linear superposition. So what we have is we have the combined potential is the sum of the potential distribution of each individual source. And that's again something that we can write in a matrix form. This is the number of channels, and this is again the number of sources. But rather than having 3 dipole orientations that we have to worry about, now we have to worry about a dipole strength for each of the individual nodes in our cortical sheet. So that means that this matrix is going to be much larger than the matrix that we considered before. But again, we have the dipole strength, like as a linear vector, and we can use linear estimation using a pseudo-inverse, for example, to solve this equation given the measured potential, giving us the estimated source strength. As I mentioned, we have a distributed source model with many dipoles throughout the whole brain, and we estimate the strength of all these dipoles. However, because we have many more parameters than measurements, the data, but also the noise can be perfectly explained. And if we return to our toy example, what you can imagine is that we take our measurements and we're going to fit a model with a lot of parameters. And then this is the fit that we're going to get. And in general, you would agree with me that this is not really the fit that you want to have, because there's noise in the measurement and you don't want that noise to influence your source estimate. So that is why we, in general, will use additional constraints. And those constraints are implemented using regularization. So if we now, again, consider the model that we have. So we have the measurement, which is the lead field matrix, so the gain matrix times the source strength. We also have noise. If we take the measurement minus the model, and if we minimize it for Q, like if we try to find the optimal vector Q, the optimal vector of dipole strength, that minimizes this, the minimum is going to be 0. So what we do is we add a penalty term to this. So we try to determine the minimum given the model for the data, but also given a penalty term that imposes additional constraints on the sources. So what we have here is the dipole moment, and we can multiply the dipole moment with a matrix that, for example, implements smoothness, that expresses the smoothness in the distribution, or that expresses the strength in the distribution, or that expresses some prior belief that we have about the distribution, such as results from fMRI analysis. And then we can weigh this error term, this is the data error term, with the model error term, using some lambda parameter. And it's always a bit tricky to find out what the optimal lambda parameter is, but there's ways for that. And using such a model, you know that you won't estimate your data fully, but you're going to get a more robust estimate of your measurement. The final family of source reconstruction methods that I want to deal with is spatial filtering, and I will only deal with this relatively shortly. So spatial filtering, or a beamforming, is the most popular version of spatial filtering. We don't estimate the position of the source as such, but we manipulate the filter properties, but not the source properties. Rather than making an explicit assumption about the source, we make an implicit assumption that the source can be explained with a single equivalent current dipole. And we make assumptions about the data. Like we say, well, there can be multiple sources present in the data, but if they are sufficiently uncorrelated, then we can come up with a method for estimating each source separately. So let's consider this example. So here I have a display of the head, and I have 2 sources, like the blue one and the purple one. And they're both being mixed, like we measured the linear superposition. And what we were looking for in beamforming is a linear combination of the data that we record on all these channels, which, when multiplied with the potential distribution of this source, gives us a strength of 1. So we're looking for a filter that has unit gain. It's like, given a model for this source, we're looking for a filter that would give us that source back with unit gain. At the same time, we're also looking for a filter, or like during the same analysis, we might also be looking for a filter at another location. And also for that location, we have the same constraint. But what we want to do with spatial filtering is not only have a unit gain constraint, but we also want the spatial filter that we construct for this source, we want it to be selective for that source only. So what we say is we want the filter for this location, we want it to suppress the activity that is also present in the data, other activity. That is something that Svetlana will explain this afternoon in more detail. So far I've been mainly explaining like the different spatial assumptions that we have about that we're making use of in source estimation. But let me also spend a little bit time on estimating the time courses, because the whole point in using EEG and MEG is that we're interested in the timing of what the brain is doing. Of course, space helps us to interpret the data, but it's timing where EEG and MEG really shine. And what we in general have is we have a linear data model where we have the measurement, which is a gain matrix times the sources plus some noise. And I should, and where we have linear superposition, so we have the gain matrix, the spatial distribution for source 1 plus the spatial distribution for source 2, etc. So it's a linear superposition of many sources. And I should mention that I realized this morning that I'm using these letters differently in the various slides, and also this afternoon Svetlana is going to use again different letters. So please don't pay too much attention to the letters because they vary, but try to understand what they mean. So if we consider dipole fitting, what we have is we have our measurement, which is the linear superposition of the activity of many sources, and we assume that n, that the number of sources is typically small. So what we can do is we can take our measured data and we can make a model for the data, and we subtract the model from the measurement. That gives us the residual. And of course we're going to change this gain matrix, we're going to recompute it from multiple source locations, and we're going to see whether we can make the residual as small as possible. But then what we quite often do in dipole modeling is that we start with one dipole, and then we realize, it doesn't really explain the data very well. So then let's add another dipole. That's sequential dipole fitting, and it's actually one of the strategies to build more complex dipole models, starting from the notion that in event-related potentials, the early activity is typically the central activity, which comes in only at a few locations. And the later you go in time, the more higher order areas are getting involved in event-related potential. So by starting early in your ERP, you know that you can model it with 1 or 2 dipoles, and then you start adding more dipoles if you progress in time. And of course, you can build arbitrary complex dipole models like this. However, if you look at this equation, what we have is we have the measurement minus the model data as the residual, and we know I've already showed you is that the estimated source strength is a weighting matrix. Typically, it's the pseudo inverse of the gain matrix times the measurement, and this is basically this is the way that you compute a pseudo inverse. Let's look at the second family of source reconstruction methods, where we use distributed source models. So here we assume that n is typically very large, like much larger than the number of channels that we have recorded our data from. So again, we have the same data model, but what we now do is we say, well, we have a matrix G, and we're going to use this matrix G in order to estimate X, like our source strength. And we're going to choose the inversion procedure such that we minimize both the data term plus some penalty term on the model. So we're going to compute W, a unmixing matrix that when multiplied with the data gives us the source estimate. With beamforming, we basically use the same strategies, except that we're not assuming that there's only a single or a few sources. We're not assuming that there's many sources, but we basically want to work with an arbitrary number of sources. So what we start with is just considering a single source, and we say, well, all the rest of the activity that I recorded, I'm not interested in it. So let's just treat it as if it were noise. So what we then do is we have a measurement, which is the activity of one source plus noise. And noise is not really noise, but noise is just all the activity that's not coming from the source of interest. And that's something that we can repeat for the second source and for the third source, etc. And for each of the locations where we take this consideration, we can compute a spatial filtering matrix, where this afternoon will be explained that this is the way that you can compute it. So at this moment, it's not really important to understand these equations. But what is important is that we for estimating source time course activity, we're always using an equation like this. So we are always saying, well, the estimated source strength is some sort of a linear unmixing matrix times the measurement. So the source activity is a linear unmixing of the measurement, similar as like the measurement is a linear mixing of the source activity. And the source activity is of course time dependent, and the measurement is also time dependent. And what we often assume is that this unmixing matrix, that it's stationary for the time of our recording, for the time of this data segment that we're analyzing. And then depending on whether we assume a few sources, this unmixing matrix is going to look different. So we have one for dipole fitting, we have one for minimum norm estimates, and we have one for beamforming. But in all of these cases, the source estimate is always a linear unmixing of our channel level data. And that is important because that's something that we also rely on in estimating network activity. Of course, here I'm showing the source estimate as a function of time, but I could also consider this in the frequency domain. So if we just think of the data being represented in the spectral domain, as like this morning you've been practicing with it, yesterday you had the lecture. So for using Fourier decomposition, we can describe the real valued and the imaginary valued, like the cosine and the sine components of an oscillation. And that oscillation can be measured at like multiple instances in time or in multiple trials. So if we consider the measurement to be a function of frequency, then you can also imagine the source estimate to be a function of frequency. And again, here we can use the same method, so we can use dipole fitting, minimum norm estimate, and beamforming, both in the time and in the frequency domain, because it's just a linear mixing and a linear unmixing problem. So to summarize, I've explained forward modeling. Forward modeling is required for the interpretation of scalp topographies, and as soon as you're going to do an interpretation of a scalp topography, then you're basically doing forward modeling. Like if you say, well, I see activity on the vertex electrode, so therefore I assume that the source is at a specific location, that's already source modeling. These mathematical techniques that we have available in forward modeling and inverse modeling, they aid you in doing this interpretation of the data. In inverse modeling, we make model assumptions for the volume conductor. We make model assumptions for the sources, and typically we would say, well, the source can be described using an equivalent current dipole. And then we make additional assumptions on the source. For example, we say, well, there's only a single source, or there's only a few sources, but not too many of them. Or we say, well, there's activity everywhere, like I already know where it is, it's in gray matter, and the only thing that I care about is estimating its strength. And then we can use different mathematical approaches. So we can use dipole fitting, where I explained that with dipole fitting we have a linear part estimating the strength and the orientation, and we have a nonlinear part where we estimate the source position. For distributed source model we have linear estimation, and in linear estimation we always use some sort of regularization to make sure that we are not explaining the noise in the data, but that we're only explaining that part of the data that we're interested in. And there were spatial filtering techniques where we're not trying to explain all the data at the same time, but where by basically iterating over many different source locations in the brain, for each of them we're trying to estimate the source activity independently. In the end, source modeling is about disentangling the superposition. So what we have is we have these measurements. We have these measurements on the scalp, and these measurements, they are a superposition of the source activity. So the questions that we're asking are not only where are the sources that are represented in this channel level data, but also what's the time course of the sources. So what we're trying to do with EEG and with MEG is also trying to get clean time courses at the location of interest. And source modeling helps us to interpret the location, but it also helps us to disentangle these time series. And disentangling these time series is important for connectivity analysis. So I think that those are the two aspects that you have to consider for doing source modeling. On the one hand, help you to interpret the data in terms of position, and on the other hand, help you to interpret the data better in terms of the temporal dynamics of the activity that you're recording. Okay, thank you.